Hi, this is Yash Anarase, and today I'll be explaining you the oxygen hemoglobin dissociation curve. The air that we breathe in contains about 21% of oxygen. This oxygen must travel to reach all the tissues of the body. Out of the available oxygen in the alveoli, about 97% is transported with the help of hemoglobin in the RBCs, and a very small amount of about 3% is transported in the dissolved form. Hence, under normal circumstances, oxygen is carried to the tissues almost entirely by hemoglobin. Hemoglobin is a conjugated protein made up of 4 globin subunits and 4 heme groups. Each heme group can bind one molecule of oxygen. Therefore, each hemoglobin protein can carry up to 4 molecules of oxygen. This hemoglobin exists in two states. T state, that is the tense state where the hemoglobin has low affinity to oxygen and is hence deoxygenated. On the other hand is the R state, where the hemoglobin has high affinity for oxygen and is therefore oxygenated hemoglobin. Now, in order to understand the transport of oxygen, we need to understand that the affinity of hemoglobin to oxygen depends on the partial pressure of oxygen at that site. That means, whenever the partial pressure of oxygen is high, like it is in the pulmonary capillaries, oxygen will be attracted towards hemoglobin and hence the blood will be loaded with oxygen. And wherever the partial pressure is low, like it is in the peripheral capillaries, oxygen will be separated from the hemoglobin and hence will be unloaded from the blood. Now when we plot this relationship of partial pressure of oxygen and percentage of hemoglobin bound to oxygen, which is known as the percentage saturation of hemoglobin, we will find that the percentage saturation of hemoglobin progressively increases as the partial pressure of oxygen increases. This is known as the oxygen hemoglobin dissociation curve. If we trace the partial pressure of about 25 millimeters of mercury, we find the hemoglobin to be 50% saturated at this point, and this is known as the P50 value of hemoglobin. Similarly, at a partial pressure of about 100 millimeters of mercury, hemoglobin is 97% saturated. On plotting these points, we obtain a sigmoid shaped curve. The sigmoid shape tells us that the oxygen affinity increases with the number of bound oxygen molecules. In other words, binding of the fourth molecule of oxygen is going to be a lot easier as compared to the first, and this property of hemoglobin is known as positive cooperativity. This property is lacking in other oxygen binding proteins like myoglobin because, being a monomeric structure, it can only bind to one molecule of oxygen. Now, the arterial blood, that is, the oxygenated blood leaving the lungs, will have a partial pressure of about 100 millimeters of mercury, and thus hemoglobin will be fully saturated with oxygen. Whereas, blood in the venous capillaries will have a partial pressure of 40 millimeters of mercury, and thus hemoglobin will only be 75% saturated. Speaking of the oxygenated blood leaving the lungs, we now know about its partial pressure and its saturation. But can we calculate the actual volume of oxygen traveling? That should be pretty easy to calculate. We know a normal person has about 15 grams of hemoglobin per 100 ml of blood, and 1 gram of hemoglobin can carry 1.34 ml of oxygen. Therefore, 15 grams will carry? Correct. 15 multiplied by 1.34, which is about 20 ml of oxygen, which also translates as 20 volume percent. This is true when hemoglobin is 100% saturated, but normally hemoglobin is 97% saturated. Therefore, it will carry 19.4 ml of oxygen instead of 20 ml. Now, the question is, how much of this 19.4 ml oxygen in the blood will be delivered to the tissues? The blood leaving after oxygenation has 14.4 ml of oxygen still left with it. So, 5 ml of oxygen per 100 ml of blood will be delivered to the tissues. Now, what are the factors that can affect the affinity of hemoglobin to oxygen? First, let's look at carbon dioxide and pH. During aerobic metabolism, like exercise, CO2 is produced in the tissues which diffuses into the blood during gaseous exchange. This leads to an increase in the blood CO2 levels. This carbon dioxide combines with water and with the help of enzyme carbonic anhydrase forms H2CO3, which further dissociates into bicarbonate ion and hydrogen ion. This increase in hydrogen ion is going to decrease the pH. Although CO2 and hydrogen ion can bind to hemoglobin, they do not compete for the same site as oxygen. Thus, they tend to stabilize the T state of hemoglobin, which has low affinity for oxygen and hence forces the unloading of oxygen from hemoglobin. This phenomena of shift of curve to the right in response to increase in blood CO2 and hydrogen ions is known as Bohr effect. Next up, let's look at a compound known as 2,3-diphosphoglycerate, which is a metabolic byproduct of glycolysis. There is increased production of 2,3-DPG in hypoxic conditions. This leads to binding of 2,3-DPG to hemoglobin, which further leads to unloading of oxygen from hemoglobin. Temperature can also alter this affinity. It affects the strength of bond between oxygen and hemoglobin. This again leads to stabilization of T state. Even few degrees of altered temperatures can affect the affinity. Another factor is the type of hemoglobin. The fetal hemoglobin has a higher affinity for oxygen as compared to the adult hemoglobin, thus binds to hemoglobin more strongly. So summarizing, in adult hemoglobin, increased PCO2, increased 2,3-DPG, increased temperature and a low pH favor more unloading of oxygen to the tissues and thus shift the curve to the right. Whereas decreased PCO2, decreased 2,3-DPG, decreased temperature, high pH as well as fetal hemoglobin favor oxygen binding and thus shift the curve to the left. Please note that these factors affect the affinity for oxygen but not the capacity to bind oxygen. That means this molecule of hemoglobin can still bind to 4 molecules of oxygen, but how easily it does so when the PO2 is dependent on the circumstances. Now, let us have a look at some applied aspects. First, let us look at some alterations when we exercise. During exercise, there is increased PCO2, increased temperature, increased hydrogen ions, and as a result, low pH. So, where will the curve shift now? Yes, the curve shifts to the right, meaning oxygen is unloaded in the tissues that need it the most. This is well evidenced by the fact that during exercise, oxygen delivery increases by almost 20-fold in well-trained athletes. Now, can you guess what will the curve look like in cases of carbon monoxide poisoning? Well, hemoglobin has 250 times more affinity to carbon monoxide as compared to oxygen, and it will bind firmly to hemoglobin to form carboxyhemoglobin. This decreases the binding sites available for oxygen. Hence, the affinity for oxygen increases at sites not occupied by carbon monoxide. The curve will now flatten out depending on how saturated hemoglobin is with carbon monoxide. For example, if hemoglobin is 50% saturated with carbon monoxide, it will flatten out after reaching 50%. Now let's quickly summarize. The oxygen hemoglobin dissociation curve shows us how the hemoglobin saturation with oxygen, or the SO2, is related to the partial pressure of oxygen in the blood, that is the PO2. The sigmoidal curve is as a result of positive cooperativity, which increases hemoglobin's affinity as more oxygen molecules bind to it. Factors like partial pressure of carbon dioxide, pH, temperature, 2,3-DPG, as well as fetal hemoglobin can all affect hemoglobin's affinity, causing a shift in the oxygen hemoglobin dissociation curve. We also saw how exercise causes the curve to shift to the right, and also how the curve of carbon monoxide will look like. And there you have it. Everything you need to know about oxygen hemoglobin dissociation curve. So, until then, stay safe, stay happy, and keep learning. Thank you.